Hello, chemical geeks. I am SquidChem, and I'm here to teach you about spin-spin interactions. Now, this is just a fun tutorial. It's nothing serious. I'd like to put that out there, just so you know it. But anyways, in this tutorial, we're just going to be covering the very basics of quantum chemistry, and that would be spin-spin interactions. And I'll also do a bit of review for things like electron separation fields and all that fun stuff. Now, I want to do a bit of review right now before we actually get into spin-spin interactions, and that is what are things like Bohr model. So let's start off with the Bohr model. So suppose we have a Bohr model, and so this is a Bohr model. Before I actually get into that, this is the hydrogen atom modern model. That's what electrons really look like. Not like that, or electrons. Atoms is what they really look like, and they sometimes look like this, and they're usually in 3D space. But that's basic. That's just basic chemistry. But anyways, suppose we have some electrons. Now, electrons do not occur here. They don't occur on the line. That's not how it works. How it works though is oh Jesus. That's not what I meant to do. Alright, so ugly. Anyway, so suppose we have this. The way electrons work is you have a Bohr radius, and inside this Bohr radius is the probability field of electrons occurring. That is the basic Bohr model, and that's pretty much all the review I wanted to do. Next, I want to go over electron separation fields and how electrons spin. Now, we all know that an electron can spin either up or down, and this can be represented as A or B. That is how an electron, this looks like O. That's how an electron spins. Now, if we have an atom, we have an electron here that spins up, and an electron here that spins down. And this here is the first electron separation field. This usually has like 4, just suppose we have 4. This is a second separation field, and it works kind of like that. And that's basically how spin works. So let's just get rid of all of that. And this is all stuff you should have covered in your basic high school sophomore chemistry class. This is all stuff you should have been covering then. So we have so the way this is written is we have like a 1s, right? This is the first separation field. It spins up, and then another electron spins down. We have 2p. You know, all this stuff is stuff you should have already covered. And then you start spinning down, and that's all stuff you should have already covered. Now, what we want to say is, before I actually go into spin-spin interactions, I want to cover a few things, because if you've never actually learned quantum chemistry, if you've never worked with quantum chemistry ever in your life, and because this is the very basics, you will see a symbol that looks like this. That is psi, and it looks like a little devil fork, you know, the scepter. This is psi, and this is usually equal to a wave equation. That is usually equal to a wave equation. Now, what we want to say is we want to have, in spin-spin interactions, we want to find whether or not an electron will be spinning up or down. So we want to know if an electron is spinning up or down. That's what we want to detect in spin-spin interactions. Now, we know that the probability of an electron spinning up and down is 1/2. So just finding if an electron spins up and down. Yeah, that's an electron. That's the spin-spin interaction. And the way you can view this is you have a Bohr model. An electron can either be spinning up or down. We know that, and we want to say if it is spinning up or down. So just a bit of a visual representation for visual learners. But anyways, we know that the probability is 1/2. So A or B, not if you've ever coded before, that's unnatural. A or, damn it, A or B is either up, or no, I'm sorry, I'm not thinking today, is 1/2. That's the probability that an electron is spinning up or down. So, now I'm going to write down an equation here, and this is going to be, so actually we know that A is equal to up, which is 1/2, and B is equal to down, which is 1/2. So A is up, B is down, and they're both 1/2, so if you were actually to plug this in as numbers, it'd be 1/2. The equation for spin-spin interaction is your wave equation times A times your wave equation times B plus, and this is for 2 electrons. It gets very long if you have more electrons, because this here is 1 electron. That's 1 electron plus, here's your other electron. So this is a 2 electron thing. Should I have brackets? No. I'm going to have brackets, and I have to undo the entire thing. So if we have brackets, this is 1 electron, and this is another electron. That's the basic formula for spin-spin interaction. Now, let's break this down. This here's your wave equation. So this here's wave equation. This here is your probability. This here's your electron, and this is just repeat. I'll be right down. It's my lunchtime. This is basically a spin-spin interaction. Now that we know this, so if we were to plug this in as numbers, we would have psi times 1/2 times psi times 1/2 plus psi times 1/2 times psi times 1/2. That's what it looked like if we were to plug in different numbers. And this here, the wave equation is basically it depends on your atom. So the wave equation depends on what your atom is. So if your atom is hydrogen, you would have 1 wave equation. And I'll go into wave equations in a whole later tutorial, but wave equations come in very handy if you want to do things like Schrödinger equations, which is quantum physics. So, yeah, and this is the foundations of quantum chemistry. So, I'm going to thank you all for watching. I hope you like. If you do like, please like, subscribe. If you have any questions, comments, or concerns, please say so in the comments below. And thank you for watching. Adios.